with the horses, Hannah with the goats. They're back? Yes. All right, sweet. So we have an informal definition for limit and then a formal definition for the limit. Formal definition of limit we learn in the next unit, and that's rather confusing. We're going to give you kind of the straight bones definition of this. And this means as x approaches some number a, as x approaches some number a, the function or y value approaches some number L. Okay, so there's two approaches. As x approaches something, y approaches something. It's the y value that we're approaching that we're really looking at and talking about, okay? So we're going to look at a few examples here so we can see exactly what's going on. And the first one is the limit as x approaches 2 of the function. So we're going to take a step away from this whole like slope of the tangent line thing, and we need to formulate our ideas clearly about limits. And that's what the first unit is all about. We can't say anything intelligent about calculus moving forward until we grapple with this concept of a limit. So take out your calculator and type in that function 1/2 x squared minus x plus 3. There we go. I go into y equals, I'm going to clear this stuff out. And I've got 0.5 x squared. Then what?
Minus x plus 3.
Thank you, minus x plus 3. And I'm going to zoom standard. So I'm going to zoom number 6, make sure we all have the same viewing window. We get a parabola, nobody's surprised by that, right? And so what I'm going to do, though, is if you can work with me on this, I'd like you to zoom number 4, zoom as a decimal, okay? And what's the x value approaching in this scenario? X is approaching 2, okay? And I want you to press trace. And let's just look at this graphically. As we get closer to an x value of 2, what does it look like the y value is getting closer to? It does. And sometimes people ask, well, which way do you approach it? Do you approach from the smaller numbers or bigger numbers? You can look at it both ways. If you say 2.7 down to 2.6, you can see that the y values are approaching exactly 3. And so that's the limit. Now, what's really kind of simple about this is that if you simply just plug 2 in, you get 1/2 times 4 minus 2 plus 3, or 2 minus 2 plus 3, which is in fact 3. So limits are very simple if you can just plug it in. You see what I'm saying? We know it's a very nice behaving function. The limit's 3, no problem. And so if you get a problem like that, you're like, thank you, Mr. Gens, because I really like that. Here, you know what the graph looks like. What does the square root of x plus 4 look like? Shifted to the left 4, 1, 2, 3, 4. And as soon as I just think about it, as long as it is nicely behaving, meaning it doesn't have any breaks in it, there's no breaks in it at the x value of 0. Okay, so if you want to figure out this limit, it's not very complicated. Just plug in 0, and sure enough, you get the square root of 4, which is equal to 2. And if we were to look at that on our calculator, we would see the same thing. Okay. Now, this one's a little bit different. X squared minus 3x minus 3. It says limit as x goes to 3. Okay. That graph looks a little bit different. Okay. It looks like this. over that spot right there is the location 3, 6. Now I'm going to show you how I came up with that. This is going to reference something that we talked about last year. We don't encounter this situation a lot, but it is important right now that you lean into this and focus on this. I think this is probably the most complicated example we look at during this time. But notice that if you were to go ahead and factor out, I'm sorry, I made a mistake. We'll erase it just a second. But if you factor out an x, notice you're left with x minus 3 over x minus 3. Does everybody see that? And so the x minus 3's divide off, leaving you with just x. And so therefore, the graph just wants to look like the graph of x. And the graph of x looks just like this, except it has a hole at 3. So that spot is at 3, 3. My bad. Sorry about that, folks. Thank you for the forgiveness, Rosa. Now, you don't have to type this in, but if I go to my calculator and type in x squared minus 3x, and I divide by the quantity x minus 3, and I look at that graph, notice, do you see the gap right there? That's what happens when something divides out. We get a gap in the graph. And if I approach that spot as x approaches 3, what does the y value approach? It does. Notice when I get to 3, it vanishes, doesn't it? It's okay that it vanishes. It does not have to have a value at that spot in order for the limit to exist. It's just what is the value approaching. You can see that the x values are definitely approaching a value of 3. So even though that there's no defined value at that spot, we do say, in fact, that the limit is equal to 3. Okay, as we approach this way, you can see that the y value is getting closer to 3. If you actually plug in 3, you get 0 divided by 0, which is a big problem, but we are approaching 3. And now we get my favorite one of all. Okay, sine of 1 over x. I love this. This is like my favorite function ever. Type in sine of 1 divided by x. Everybody make sure you have that in your calculator. And we're going to do a couple things here. The first thing we're going to do is we're going to check in mode to make sure that we're working in radians. Again, I said everybody should be in radians. And finally, we're going to zoom 6. We're going to zoom 6, zoom standard, and that's our picture. Everybody okay with that? Now, if we want to know the limit in this problem, saying the limit as x goes to 0, notice if you plug in 0, you get sine of 1 over 0. Are we allowed to divide by 0? No. Maybe we can still figure out the limit, but as I look at this graph right here, it's hard for me to think about what the limit would be. So I'm going to zoom in. Press zoom, and we are going to choose number 2, in. And I'm going to highlight the origin and press enter on it, and I'm going to produce a new picture. Now that we have a new picture, is it clear to you exactly what the limit is approaching? What if you were to take a guess? What would you say? I would guess 0 as well. It looks like it has a top, it has a bottom, but I would like to be more confident. So I'm going to zoom again. I'm going to zoom number 2. I'm actually a little bit less confident than I was before. What if I zoom in again?
Yeah. No. Let's zoom back out. Just not deal with it.
I'm going to try it again.
Okay. It is just gonna get worse. It looks like my screen got broken. I'm boxed.
I'm not convinced this is going to 0. What does it look like? Barcode. It's actually called the barcode function. As you zoom in an infinite number of times, you actually produce every time a unique barcode. I've always wanted to like put this on my calculator and then go up to the store and like scan it and see if I would get a price on it. But yeah, you get a unique barcode every single time. It'll be different every time, and you can see that at no time does it look like it's headed towards one exact value. This is very complex, and if we looked at the function from the beginning and analyzed sign, sure enough, it would tell us a lot about why it does this. But barcode after barcode after barcode. And thus, in this situation, we don't see it headed towards one single number, and so we therefore say that the limit does not exist.
Oh.
The limit does not exist.
Should we go to a field trip to the store? Big lots.
Which I believe is a quote from Mean Girls, which we are celebrating this year in the musical. Raise your hand if you're going out for the musical Mean Girls.
Danny is.
Awesome. Danny is going out. Rose is going out. Ava. Ty is going out. Attaboy. You can do the rap. Let's go. So, in order for a limit to exist, the left side needs to be equal to the right side. We're going to talk about one-sided limits, okay? One-sided limits. A left-handed limit says as x approaches a from the left, okay? From the left. So if you have a negative sign right above that value that x is approaching, or if you have a positive sign up above, it means that you're just looking at the limit from one side. So we talked about, do you approach from a bigger value or a smaller value? This tells you right there, okay? So the first thing that you're going to have to do in this lesson and on your worksheet, and something you're going to have to be able to do for the test, is to be able to look at these graphical examples, okay? And so this one says the limit as x approaches -4 from the left. So I'm going to approach -4 and I'm going to go from the left. I want to think about the y value. As I get very close to -4, what does the y value get close to? It does get close to +3. Is everybody okay with that? And notice it's filled in at 3 as well. In this situation, I had close to -4 from the right. What is the output getting close towards I have from -3 to the right? -2. Notice how it's an open circle. You can have a limit at a filled in circle. You can have a limit at an open circle. See that? This one, limit as x approaches -1 from the left. So I'm going to -1 from the left. What's the output approach? 4. Good. And now I'm going to approach -1 from the right.
Still 4.
4. Limit as x approaches 2 from the left. I approach 2 from the left. -1. I'm now going to approach 2 from the right. 5. What is different about question G compared to the other questions? It doesn't say left or right. That means the limit as a whole. It means left and right. And so here's what we do. The left is different from the right, isn't it? If the left and the right are not the same, then the limit does not exist. So a more formal definition of the limit, if the limit as x approaches a of f of x is equal to L, if and only if the limit as x approaches a from the left is equal to the limit as x approaches a from the right. And those are both equal to L. The left and the right must both be the same in order for the limit to exist. Okay? So we look at letter H. The limit as x approaches 4. Is that a one-sided limit or a two-sided limit? Two-sided. So as I approach 4, I need to approach from the left, and I need to approach from the right. From the left, it's approaching 2. From the right, it's approaching 2. So therefore, the limit as a whole is 2. Is that clear? Okay, excellent. That's the concept of a limit. It says, note that f of a does not have to be the same as L. So in this situation, just want to be clear, suppose that we added a point here. Notice how there's a hole there. Suppose it was filled in here. Our limit would be 2. It would turn out that f of 4 is actually 5. Just because it has a hole there, that doesn't mean that's what the limit is. The limit is what you are approaching, so it can have an open circle. Is everybody clear? Excellent. Take out your calculator and type in x squared minus 4 over x minus 2. And what we would like to do in this situation is it says use a table in order to determine the following limits. So if I plug in 2 to this situation, I get 0 on top, I get 0 on the bottom. So we are going to go to our calculator and try to figure out what that would be. I go ahead, I'm going to press graph first, and I'm not zoomed in correctly, so I'll zoom 6 to zoom standard, and I'll actually zoom decimal now, okay? But you can see, as I trace, as x approaches 2, what do you think the y value is approaching? 4. So what we're going to practice is with our table, and this is very important, that you approach both from the left and from the right. So if I'm going to approach 2 from the left, what value should I plug in? 2 from the left. 1. Good. Then? 1.5, then 1.9, 1.99 or 95, sure. Anything that's getting you closer. And as I type this in, it appears to me that the y value is definitely approaching 4. Now I'm going to check from the other side. If I want to approach from the right, what values do I plug in? Sure, 3. Then 2.5, 2.1, 2.01, 2.001, so on and so forth. You can see that the evidence shows us both from the left and from the right that it is in fact approaching 4. So we've determined that the limit is 4. Go ahead and do letter B on your own. Do letter B on your own. Okay, so these are the values I'm looking for you to approach with, somewhere around there. But eventually we get very, very close to zero, so negative 0.001 and it's positive 0.0001. Either way, the limit is 1. And this is actually an extremely important limit that we use throughout the rest of calculus. We'll come back to that quite often. We good? Okay, last part. Examine the limits of the following functions. So you should be able to type it into your calculator, or you should be able to look at the table. I happen to know the graph of 1 over x to the fourth and what it looks like. It looks like this. It's a reciprocal function like that. Okay? This is slightly different. We'll see who can come up with it. Okay? Asking you to think a little bit outside the box here. Limit as x goes to 0. Notice it's going to be a double limit. I approach from the left. As I get close to 0 from the left, what happens to the y values? Yeah. What do you think I'm approaching from the left? Yeah. How about from the right? Are those the same? They are. So the limit is infinity. In this situation, I know I have a vertical asymptote at x is equal to 1. I can see that it's undefined there, and I can also see that it does not divide evenly. If you wanted to go ahead and get the rest of the shape, you could type it into your calculator if you needed to. I'll do 2x plus 3. 2x plus 3. I'm going to divide that by the x minus 1. And you can see from your graph that it's going to be in the bottom and then in the top in this situation. We're going to be in the bottom, and then we're going to be in the top. So I'm approaching 1. As I approach 1 from the left, what is the output approach? Negative infinity. And as I approach 1 from the right, positive infinity. Are those the same? Definitely not, so therefore the limit does not exist. The limit as x goes to a, the function is equal to infinity in plain terms just means that as x gets closer to a, the function gets very, very large. If you have an infinite limit, you're going to have a vertical asymptote, okay? So if x equals a is an equation for vertical asymptote, then one of the statements must be true. Either the limit as x approaches a of the function is equal to infinity, or the limit as x approaches a of the function is going to be equal to negative infinity, or the limit as x approaches a of the function does not exist. And we saw in 2 examples there that involved infinity. In one situation, the answer was infinity. In the other situation, it did not exist. So if you have a vertical asymptote, that's what's going to happen. And to wrap this up, what is the equation for the vertical asymptote here? Vertical line, x equals or y equals? X equals. So x equals 0 is the equation for this vertical asymptote. Notice how it produced an infinite limit. And in this situation, x is equal to 1, the vertical asymptote that in fact produced that it does not exist scenario. Got it? So tomorrow you have time to work on this assignment as well as the previous one. I will not be here, so make sure that the answer key is posted. You see the first answer key is up there. Please make sure you got those things knocked out, ready to go. After this, we have 2 more lessons. So we'll cover a lesson on Wednesday and Thursday. I'll get you your study guide, and you'll have time on next week, Tuesday and Wednesday, to ask questions. We'll test on Thursday.